I'm really happy to be the person to introduce my friends here actually. I always keep on saying it's like family, isn't it? You always meet the same people. They may change business cards, but it's always good to really meet and chat with familiar people, places. So today we have an extra panel here. Possibly I do not need to introduce each of them, but of course you know Eddie from Bloom Energy. You know of course Mr. Data Center himself, Jon Summers, from the Rice Institute, and last but not least, a good friend of mine, the smartest engineer I met so far in the industry. I'm around since a while. David Gyulnazaryan, also known as David G. And so enjoy. And by the way, this session is being recorded. More people are joining. I'm happy. Welcome. And Nico today is audience. And I think Eddie, you're keeping on with some slides.
No, I was going to get Jon
We planned. I was the moderator, so I was going to start, and then Eddie's going to show some slides. We haven't rehearsed this, so let's see how it goes. So, well, I thought maybe we need to do a bit more introduction. So, my name is Jon Summers. I work at Research Institute of Sweden. I've been working, formerly an academic, working in thermal management for well over 12, 13 years. I think, David, you watched me immerse a mobile phone many years ago when we were messing around with the isotope systems. So I've been messing around with liquid cooling for a long time. We've been doing a lot of research on that. And of course, the liquid cooling has always been, one of the arguments has always been that this gives you a much better opportunity to recover heat if you're in liquid phase. And maybe we'll touch upon that in this panel discussion. So let me hand over to you guys to introduce yourself a bit more. Eddie, do you want to go next?
So I'm Eddie Kilbane. Been involved in the data center industry for 20 years, mostly as a phenomenal operator, also working there with other data center operators as they were building out their infrastructure. And for construction, so my role has been building, physically building, and so nothing on the IT side, but certainly very involved in handling our cooling our data centers. In Ireland, the market is very strong in terms of who's present in the country, so economics, realty, etc. So our company in Dublin had to be very niche, very unique. So we were pushing the boundaries of cooling on the largest databack. HO wheel in Europe is an installation in Dublin, full 2 to 3 megawatt data halls, no mechanical cooling, again here in Dublin. So we would do things like that to attract our customers and clients. And from there now, I'm now working with Bloom Energy, helping the system then come into the Irish market. We're sold alongside a fuel cell company, and what we do is they provide a solution for gas, biogas, or hydrogen to come in, mix over fuel cells, and then produce electricity. But it's a massive offtake of waste heat, which is heat capture, so I can show you later on some slides how that's done.
Thanks, Eddie. So, David, Mr. Combined Heat and Compute, introduce yourself.
So, my focus in that's decarbonization and heat reuse, and the opportunity of heat reuse is the make impact out of the scope of data center influence. So, when we substitute the third-party fossil fuel using, then magic is happening. That we provide thermal energy, not to the ambient, but to the right useful direction. And also, I work with Open Compute project because the open source solution can drive that another way of thinking for legacy data center business.
Okay, right. So let's get started. I want to take you back to 1961 in July. A famous guy who worked for IBM called Ralph Launder. He wrote a very famous paper. It was called Irreversibility and Heat Generation in the Computing Process. So we know that what we do in terms of compute has a consequence. And today we know this. We're trying to get more efficient with our compute, but unfortunately, you put every watt of power that goes into the electronics is transformed. I don't think it's consumed, it's transformed into another form of energy, which is thermal energy. And so there's a great opportunity here. I mean, the title says opportunity for heat recovery. And of course, this is a topic that's been discussed for many, many years, heat recovery. And one of the biggest issues we have is you need somebody to take the heat. And I think that's been mentioned in a couple of panel discussions today. So it's a lot of joined up thinking, it's a lot of collaboration, and there are some great examples of it, of heat recovery. And most of those that I've seen where they are connected to a district heating network, which is one of the, where the heating network is working all year round. We can talk about seasonal disadvantages a bit later, but that usually involves a heat pump. And I can list quite a few, but I wondered whether you guys could give us an example of a good heat reuse, recapture and usage example from your walks around. And I think, Eddie, is this a good time to talk about this? The fuel cell example. Okay.
So Blue Energy, as I said, is they make fuel cells. So these grey boxes here are the cells themselves, and this now is connected to a heat exchanger where they're now taking waste heat. This is a 330 kilowatt installation, providing 300 degrees of heat as part of its waste. So these are the cells, and this is the 300 degrees. Then we take it off it. It goes through the client's heat exchanger, and that client in this instance is using it for 73 degrees. Their return temperature 65. But at 300 degrees, now you can look at absorption chimney. You can use that now for lots of other things in a data center to add to that data center mix that's coming from the data halls. We were talking earlier with some of the guys about 40 degrees coming off the servers as part of the chip cooling. So if you mix that with this, now you've got usable heat. It will either go to a district heating system, go into processing, go into other structures. This is the very last slide. Next. Thanks. So this is the back of the unit. So it's clean, very simple installations. We have 2 openings out of each of our cells, and those then go to the central pipe network, which then goes into the back of the containers, then continues on then for the internal process for that particular customer. That customer's a medical devices company, and so they're using that waste heat for something within internal processing for their manufacturing. Very simple to install, very cheap to recover, and has massive benefits then for reusing them outside.
So yeah, I mean, Bloom Energy does have quite a lot of installations in the US for data centers, but the heat recovery is more of a new thing in this particular instance.
So in the US, the drivers in America are a lot different to the drivers in Europe.
Yeah.
I think from our carbon capturing to our heat reuse, this is more being developed now for the European market, but it is being exposed to the US.
Yeah.
So there's a number of installations going on. Myself and my colleague, we're talking to a number of companies in Ireland and Northern Ireland and in the UK about installing this very system. Some of it's for drying grain, some of it's for keeping molasses warm, as well as then having the energy on site then for producing electricity. The efficiency of that between the electrical efficiency and the thermal efficiency is at 90%.
Yeah. I mean, the fuel cells are the solid oxide fuel cells, because they're high temperature fuel cells, are very good at that. Yeah. And I guess it's it's about the cost, the price per kilowatt.
So the price per kilowatt on a 5-year term for one of our installations is about 38 euro cent per kilowatt hour. So it's more expensive than the grid. We're never going to be cheaper than the grid because we don't do these things at scale. But if you look then at what you're recovering, what you can move on, and the fact you're efficient as well, we can capture the carbon and the gas as well, so we can actually have that as an option.
Yeah, at source. Yeah, it's easy to.
We're taking in a fossil fuel, we're taking out the CO2 element of it, and we're now producing clean electricity for our customers.
Yeah. Okay. So the next stage really is you have a heat source from the data center as well. If you were supplying this, so you have the 2 heat sources at different temperatures, And you reckon that would be a good argument for an absorption chiller then?
So
Yeah.
what we're talking about is that if you're capturing it at 40 degrees, you're still going to need to put a heat pump on that to get to 60 or 70.
Yeah.
It's then usable in the heat system.
Okay. Yeah.
So, this negates all of that. So if you're taking your recovering at 40 degrees out of the data center, you mix it with this 300 degrees to get to the 70, you don't need a heat pump. You just need that heat transfer between the two systems.
And what about the argument? I mean, it's running on gas at the moment, but natural gas, I guess. But I think the future is probably using a renewable form of gas. Yeah.
As in when we run on hydrogen, we don't have any CO2 emissions. So this is a hydrogen fuel cell. In fact,
It's hydrogen, yeah, but it's gas. It's natural gas at source. But then you can mix, you can blend the gas. Okay, yeah,
It's the same
yeah.
technology. So
Okay.
it's really mind what the format of the gas is.
Okay.
Clearly, gas can be coming from landfills and things like that. It's going to be rough and everything. You need to have that cleaned. That's just the skids to take
Yeah,
that gas before it
yeah.
comes in.
Yeah, and I think it's a good argument for using biogas. But why are they going to put carbon tax on biogas? I guess is a bit of a tangent, but that's something we need to think about as well, because the carbon's already in the atmosphere. Yeah, when it goes through the system.
Yeah.
Well, thanks for that. Yeah, okay. David, I think you have some great ideas, some great examples of heat reuse, don't you? Yeah.
Yes. If we look for real heat reuse, big scale examples, they are in most cases connected with the air-cooled data centers, so low-grade heat and heat pumps. But the exciting examples, they are in small scale on rack level for testing, but with immersion and on-chip cooling. So in case of immersion cooling, we have lower temperature than with on-chip cooling, because in case of tank, we should have average temperature, which should be lower, because all components also, which is not so hot in semi-environment. But when we have on-chip cooling, we have the deal with most hottest part of the server, which is CPU and GPU, and the temperature of them can be 80-90 degrees. So potential for the liquid form can rise up to 70-75 degrees. And we have such examples on rack level. But on big installation, we didn't achieve yet. So the flexibility for data centers is to have end air cooling and on-chip cooling and immersion cooling. And in that case, we will have, of course, lower temperature. And as said Eddie, the fuel cells and this high-grade heat can be complement in order to avoid heat pumps, and it will perfectly fit to rise up this not enough level of 55-60 degrees to which is requested by district heatings or other process industries, to rise up that just for 10-15 degrees, and it will be perfectly synchronized system.
We've got some on-chip cooling testing with Rise 3 years ago now.
Yes, about 3 years ago. Yeah.
So we were testing up to 70 degrees of temperature.
Yeah, it was over 60 degrees that we managed to get off there, yeah. But it was older technology. That's the problem, I think. The problem we have at the moment is that the newer technology is the temperatures, the T-case temperatures are going down. So the argument I've been making is, I mean, it's great with old technology, but with this newer technology, with the T-case temperatures, I'm not sure 80 or 90 degrees is probably GPUs, but if you look at, and this is where I give you a real life example. There's a high performance computing data center in Finland, which is our largest one in Europe, a supercomputer. It's the Lumi data center, and they have 3 heat pumps underneath the data center, which is upgrading the heat from direct to chip applications. They've got the latest technology AMD processors in both the GPUs and the CPUs. They can't go any hotter than 32 degrees supply temperature to the CPUs, to the microprocessors. So they only get 44 off, and then they upgrade that to 85 to the district heating network. And actually the data center can provide, in the summer, sufficient energy for hot water for the whole population of Kajaani. And but in the winter, obviously, they don't supply at all. It's a 10 megawatt data center. So, and that's the other problem, is the seasonal aspect of this. So, going for liquid cooling does give us advantages because we have the heat in the liquid phase already. So I agree with you on that one. But
if you look at the temperatures in the UK and Ireland,
yeah.
They're not going to have the same extremes that we have in Finland or the Nordic countries in terms of snow and such.
Yeah, I agree.
So it's going to be easier to manage that base load and actually program that into your district heating systems.
Yeah.
And much easier to manage them.
Yeah.
What we are seeing is, in the project that we've been involved in recently, is that the site we're going to have all the video servers in it. Day one, they were starting at 20 kilowatts, and in the same footprint, same server, same rack, it was going to go to 30 kilowatts. And they were insisting that we have on-chip cooling day one, and they had CDUs in the base of the rack, and then we had a centralized CDU then in a corridor or somewhere else to then read that on as part of the area management system.
Yep.
And so we were seeing that, and that's a company that's got 18 of these data centers in the US, and now they're going to expand into Europe.
Okay, yeah. So another example is, this is an example in Scandinavia against Sweden, is there is the Stockholm Exergy, the network in Stockholm. There's a data center company that has two data centers. One is attached to the south part, one attached to the north part. One, they own the heat pumps, the other one, they don't own the heat pumps. And one part, they can only reject the heat. They're only allowed to reject the heat between September and May. So what do these guys do when they have to reject the heat? You can't use the heat in that. So it comes to this seasonal aspect. Heat is very seasonal. So I don't know whether you've got something to say about the seasonality of heat recovery and what kind of technology we need to bring into the realm in order to manage this, so that we're not throwing away megawatt hours of thermal energy as we are doing, probably gigawatt hours at least anyway, terawatt hours. That's what it is of thermal energy as we're venting to atmosphere today. So what do you think about the prospects of thermal storage then? What can we do there?
So there is 2 points of view. One point of view of the data centers and second point of view of the heat user. So if I am owner of the building and I consume for the winter, let's say 300,000 cubic meter of gas, and from this 300,000 cubic of gas, that center substitute all of them when I'm happy. And I don't care that during the summer they release heat to the environment. So from that point of view, everything is great. If that center substitute all the fossil fuel consumption of the city, that we achieve the target. But the point that we can go further, and we can create some applications where we can deliver that heat in a usable way in order to avoid additional energy consumption by pharmacy or other processes which can be stored and stopped and used only in the period of time when we have this on-demand heat rejection. So it's a way of comprehensive thinking and including in that also other industries. And also we should stimulate district heating operators, other industries to, before use fossil fuel, use till the end data center heat rejection, and after switch to the fossil fuel. But now we don't have such legislation, stimulation, and this is why it's not happening.
Yeah, okay. I mean, so what you're saying is it's better to what I'm concerned about is the fact that a data center that has to reject heat to atmosphere during the times it cannot supply the heat to the network is that it has to install extra equipment to do that. And this is an overhead on maintenance, it's an overhead on the cost. But I mean, can we combine technologies in this sense to...
Yes, yes, this is what I'm saying. Why we are pushing data centers? Why we are saying to data center do that and that, and don't say anything for the other industries, which is also have responsibility for that transition. And it's easy to blame only data center, but But we should think comprehensive. And another thing is connected with location. Many data centers located far away from the city or any industry. And we should also talk with other approach when we can make distributed data centers, which can be located in the buildings, in districts, or underground even.
So this is actually closer to the end user then. Yeah, I guess that's where, because fuel cells are very quiet.
Yeah.
I mean, those solid oxide fuel cells, I mean, that's so, but I mean, 330 kilowatts, is that what you would class as something like a more urbanized data center, an edge data center?
We've got fuel cells sitting inside restaurants, we've got in public areas. The background noise here is loud in the fuel cells when people run.
Yeah.
It's only a fan running on the motherboard. It's a different control. That's all it's running. So you don't hear the actual process itself. You hear the fans which control the motherboard. So in the development environment, they're perfect in terms of its location. Going back to the waste heat situation, there has to be that catalyst that where do you then find other sources then to send that heat to those people, those seasonal periods, Glass houses at night time still require heat at night because they're working on places that thermal gain need which they get during the day. So there is other locations that you need to have. They should be finding so that you have that distributed platform to move that heat out. In Ireland, what we're seeing now is that there's a new push by the government to start putting in distributed systems. So in Manchester at the moment, there's a housing estate going there as part of this planning application. They have to install distributed plumbing. So the developers have to put that in. And that will be connected back to a number of data centers in the Gyulnazaryan and Manchester area, the new ones that are coming online. And the waste heat from that will be going to feed it. But until those workloads goes up and the server densities go up to 20 to 30 kilowatts, at 16 kilowatts you're still getting air. It's very hard to recover the air and use that air as a meaningful byproduct. So it has to be sort of logic for it to be a usable sort of product. But again, there's that education to the planners and the government that it's all well and good saying put district heating in the future of waste heat, but probably very little they can do apart from sticking a heat exchange or a heat pump and doing it mechanically with a heat pump.
Yeah, that's a good point. Yeah, I mean, obviously we are seeing the legislation here in Europe. I think we've talked about this at a number of
every day.
I mean, in Germany, they've raised the bar in that sense to try and look at the possibility of reusing heat. But a couple of thoughts on this myself, and I don't know whether, just to be provocative here, and I was trying to mention this yesterday when you had your combined heat and compute session. And that is, when you look at the ISO PUE calculation, it talks about if you get your cooling from the street, if you like, or from a cooling network, you have to add something to the PUE because you're getting your cooling from a supplier. So you have to measure that. If you put a heat pump that's on the energy provider side, the boundary condition on the data center again is still the same. It's getting cooling, or even though it's providing the heat to the heat pumps, it's still getting the cooling from the energy supplier or the energy network that's connected to the district heating. Yeah.
Cooling as a service.
It's cooling as a service. Yeah. So, but the argument when they do the PUE calculations, that's not factored in.
Right.
I mean, calling out some of the hyperscalers on this.
It's taken in the financial documents, but not in technical.
It's taken in the financial. Okay.
District heating systems in Sweden,
Yeah.
they want to manage the heat pump. So the district heating body are actually managing the network itself.
That's right. But I
In
mean,
other parts of Sweden, so I'm working on a project just about 120 kilometers to the west of Stockholm, and there, the district heating pump has to be, the heat pump has to be owned by the district heating body.
yeah, that's true. Yeah. And that's actually, on the one hand, it's useful for the data center because you don't factor that into your PUE calculation. Because Kayani, for example, the Lumi data center, when they do their PUE calculations, they factor in the 3 heat pumps into their, because it's in their boundary condition. But But the problem is going back to that data center in Stockholm. I think he had an American client who said, "Well, your PUE, you've got heat pumps. I'm reusing the heat. I've got heat pumps, but his PUE was greater than 1.2, and of course I can't host my equipment in your data center because it's greater than 1.2. Oh, but wait a minute, I'm reusing the heat. So there's another metric which is called the energy reuse factor, which needs to come into this. But we're not doing the PUE calculations correctly, as the ISO says it should be done, and we're not using ERF at all. Nobody's using ERF. I don't hear it talked about much, the energy reuse factor. So, and it's a shame that the energy reuse effectiveness, the ERE, which was brought up by the Green Grid, never became an ISO, never became a standard, because that combines both PUE and ERF. And Raoul is shaking his head there. He obviously has something to say about that, but we'll get audience participation in a minute. Yeah. But go on, David. What do you think?
Yes, I want to say that when you have American company, they looking for the money, and for PUE, for them is indicator of the payments for that PUE. But in fact, in this case, when you make heat reuse, your money investments or payments for OPEX is actually lower. You have high PUE, but you have reverse from that heating. In that case, for the customer which comes for that data center, no matter what is PUE, his payment for colocation is lower. This is the point. So in US, PUE is indicator of your efficiency and your payment from the customer side, but in case of Finland, it's not the case.
No, well, yeah, Finland's a special case in that, because I don't know whether most of you know, but there is a tax incentive for reusing the heat in Finland. I don't know whether it's not the case in Sweden. And I don't know whether that's the case. What is it like in here? Is it?
There's no incentives here.
No incentives at all, no. I mean, that's, legislation on the one hand is saying you must do this, but then they need to give a helping hand.
There's capital gain, there is tax structures and everything for recapturing, ordinary dry coolers or crack units or whatever, so you get your capital allowances on that. But there's nothing specific about you reusing the heat. So that investment has to be made by the developer or the data center operator at their cost. So they've got to put all that in to provide that.
Okay, yeah. It's going to be interesting what the auditing. We're going to go into in the next couple of years. We're going to start see auditing in Europe of these metrics that are being used a lot, and it's going to expose some potentially interesting things. But particularly around about this.
Next year is the first.
Yeah, is the first. I think they're optimistic there to get that data, but. I mean, how are we doing for time? I think we can.
I just want
to
add one point that even with air-cooled data center with low-grade heat, we are able to build district heating by less generation. When we have heat pumps on each house level, and each house provide cooling for the data center, and instead of having 70, 90 degrees water in the loop, we will have 30 degrees, 25 degrees water, which will return 15, but the investments overall in the system will be much lower, and flexibility will be also much lower, much higher, sorry.
And that's what we're seeing in Sweden. In Sweden, they are running the district heating at much lower temperature, and then localizing it where not transmitting it to
But yeah, I mean.
We finished design, the first thing and then put more technology existing everything at 70 degrees, which is not happening in Finland or Sweden. It's now this new 40 degree less energy being wasted, losses of pipes.
This is what's classed as a fourth generation network. I mean, unfortunately, most of Sweden is actually third generation. I know that from, and actually it's hotter than 100 degrees in the middle of winter. On the supply line, in the north. But I guess Stockholm, it will be a higher temperature. Yeah. Okay.
And what is the point of that statement that data centers alone can do that? District heating also can do that. It should be much higher level, government level, which will evaluate that possibilities and explain that it's better to install many heat pumps in each house and have that way, and it can be driven only by the high level authorities.
Yeah, I mean that's the idea here. I mean they've been trying to lower the temperature because the losses are huge when you're at high temperature. So if you lower the temperature of the network, the losses are lower. But then everybody upgrading the heat at the point of use is an electrification of heat. Because if you use it, you need to use heat pumps. Yeah. Sorry. Yeah.
Solar panels.
Oh yeah. Then we got solar powers.
Yeah.
But then you can only upgrade the heat when the sun is shut. You need battery storage. That's right. Yeah. I think we've raised quite a lot of things here. But I think we got about 10 minutes left, and I think it's interesting to see whether there's any questions from the audience to our panelists here, or whether there's any thing you want us to discuss further.
In terms of deep green use, how should we ever expect to have green use and that's in the data centers? We can expect to use like a megawatt of that, 2 megawatts. Is the required to use large percentages?
Well, by example, I would go with the Kayani data center, which is all of the heat is used. So that's a great example, but you've got to have the infrastructure for that, haven't you? You've got to have the heat network, and it's an isolated case. I don't think you can do that everywhere, So, I mean, there are great other. I think Yandex was another one in Finland where they are reusing all of the heat, but they are using heat pumps to upgrade that heat. So.
In terms of sizing, when you sign it at 10 megawatts, we know that our data centers work already at 50, 60, 70% utilisation. There's also no load operation that refers to how would you expect to size that heat use? One thing you can think about, right? What's practical? You've got 10 megawatts of heat. What's the pipe size? It comes back to reverse engineering. What we put in the load to actually transfer the data center to the source. So I think the challenge is going to be more on how do we design it, and then what the requirements are. So you've got 20. So these new AI data centers, this US company looking to deploy, they're 20 megawatts. Use all 20 megawatts. This is the way they're doing it. So it's not like the old days where the client had done, you wanted 20 megawatts and used 52% of that at best. These days now you'll see full use of 20 megawatts use. So that thermal energy needs to be then designed in such a way that it can be transported to various housing estates, swimming pools, factories, using that in their own processes. So it's really, it's not a simple question. It's a much bigger scale that needs to be done. Taking a lot of what was already happening in the Nordics, Finland and Sweden, and using it as examples then of how we can build them. I think it's really going to depend on the rest of the stuff.
Well, in terms of the heat injection, you would always have to have 100% on-site heat injection. I would imagine in a data centre anyway. So the seasonal thing goes without the question. It's needed to be used, if it's not, it's been injected the atmosphere.
Yeah.
That's the way. I mean, it's work.
That installation I showed you there, the requirements only taking 73 degrees heat and 300. So the ingested rest of it is just being pulled from the top. So in a simple way of doing it, it's not the most efficient. That particular client is looking at other uses on that heat to see if they can do other things internally within their factory. But for them, they're going to save hundreds of thousands of euro in costs by not running boilers or systems that they need for that process.
Did you want to say something about it, David?
I just want to add that one of most efficient match for heat reuse is water desalination in hot countries, because water requested around year in constant volume, and all your energy can be converted to the valuable product, the water, fresh pure water, which is in Middle East, in India, in Pakistan, etc. So from that point of view, it's better to build that center there to make heat reuse, not in cold countries.
I think the problem really is that there's no blueprint for all of this. This is and every site is different. Every geographical location is different, and of course it needs a collaboration. Always, data centers can't do this by themselves. So you need, as we go back to the problem of we need the heat consumer as well, whether it's a network or anything.
You need the offtake. You need to make sure, more than anything else, you need an offtake.
You need an offtake,
At the moment, in Dublin, the data centers that get built at the moment are always asked to provide distributed pipelines to the mountain. There's nothing physically there beyond that. So there is that gap in terms of what's needed. How big is that heat pump going to be? No one knows what the dynamic temperatures are. That first project in Tala, there's a trial, they're extending it now, so that's actually going now. So I went to a local university, and now it's going to be extended on there to some social housing projects.
Okay,
so it'll be very successful, and they will build off the back of that. But there has to be a set of rules and guidelines and specifications, which at the moment currently don't exist in Ireland. So everyone's doing it on prayer. Listening to things in terms of deciding.
Yeah, good point. Yeah, Damian, I think you had a
One question I'm sorry, this discussion. The fuel cells, just obviously discussing today. I'm very familiar with the automotive sector and the fuel sector technology. Has the industrial fuel cell technology from the automotive systems now? And what size is it going up to?
So we've deployed in excess of 20 megawatts. It's the biggest one. Yeah, so it's 30 megawatt deployment already live. We've done a number of data center deployments this year in the US, 17, 20 megawatts. They can be multi-story, so we can put away frame and actually set a small. They can actually stack them in a single frame, open-sided, to make sure we have the air flowing over the capacity.
Typically, how much energy do you need to produce 1 kilowatt of electric power?
So 1 kilowatt per unit of gas will give you 0.6.
Sorry, 1 megawatt.
Yeah, so it's 0.6, so 1.6 of gas. It's 60% efficient.
50,
Or hydrogen.
55% electrically efficient. Yeah.
100% fuel celling and 7% hydrogen per angle.
Acoustics are bad. I don't know.
Speak loudly, right?
So the electrical efficiency of standard solid oxide fuel cells is around 55%. So 55% of the energy value, the lower heating value of the gas, is converted into electricity.
So we're running at 60. 55.
Come on, it's 55. Let's be realistic.
The thing is that saying
It's marketing.
there's no magic solution to all of these problems. I think it's a scenario where we're going to have to combine all the different elements, all the different numbers to find a solution with reference to sustainable based on the geographical area as well, because I think that's very important. Like stuff that works in the Middle East, stuff that works in Northern Europe, stuff needs to go work out and vice versa. And I think it's incumbent on government and industry and industrial leaders to try and do some coordinated planning, which is strategic to each location, because there's no one size fits all. I think we're all agreeing on that.
Yeah.
Right.
When it comes to deploying these heat recovery systems, again, the most important thing is the offtake is not there. And what other processes or what other things that can be done inside the data center to utilize that, to self-consume that heat which is generated? Because the data center actually wants to get rid of it.
Yeah, that's right.
And then what else can be done? Because if there is no offtake,
We're cooling power rooms, cooling UPS rooms, we're cooling the table. There's nowhere in terms of for us to use it. So, not in my experience.
I can say that there is three options. Or you bring data center closer to the heat user, or you bring heat user closer to data center, or they make both in one place from the scratch, design the ecosystem.
There's
And
two options. So,
three.
well,
Well, it's still two.
it's still. so,
That one is the best one.
the third one is the best one. Yeah.
So I'm working on a project where we're using a new form of glasshouse, which is an adiabatic glasshouse. So it's a glasshouse now that has been designed specifically to work with the data center. So we take waste heat, we take electrical energy that's not being used on a daily basis by temporary generators being started, to use all of that kinetic energy and electrical energy to heat the glasshouse and keep it cool in the summer months. It's an adiabatic system, so there's 90% less water than traditional type of glasshouse uses. It's the future. And we are talking to technical operators about physically locating these adjacent to the data center on their sites.
Yeah, we need we need good data for that, because I think sometimes there's a mismatch in the power consumption and the actual But I think your question is more related to what they used to call follow the moon policy by Google, which was push the workload to where it's night, get rid of the heat much easier. But it's actually, can we move workloads around to say, turn the thermostat down and the workload moves somewhere else, that kind of thing. Is that what you were trying to get at? Can we do anything inside the data center? I mean, the EU, the Horizon Europe, put out a funding call for seasonal storage, seasonal thermal storage. I don't know, whether the technology in thermal storage, heat storage, there are a couple that I know about that are really not that great, but they're massive engineering projects, like pit storage or that kind of thing, where you pump the heat into an underground storage container, which is huge volumes.
We have storage containers on our glass centers.
Oh, you have okay, yeah. So that, yeah.
We can see it on our site in Cambridge.
Yeah.
We have a storage tank there that takes the heat into it at night time and releases the glass.
Okay.
So we're storing the heat off the CHP that we're using.
And I want to share just one example of experience. When we talk with the customer, that center, about the heat reuse, he said, who need that low-grade heat? I have a neighbor, pharmaceutical factory, which have already 40 degrees waste heat. And I said, this is your customer. To get that 40 degrees waste heat, they use the gas. They have a gas pipeline. And instead of this gas pipeline, they can use the heat from you and eliminate usage of this fossil fuel. So you should think wider. I think that if there is already waste heat, it's not mean that you don't need. You need.
So it's collaboration. There are two phrases for this: sector coupling and industrial symbiosis, and it needs collaboration. So we need to get more than just the data center involved in this. But I think the burning question that the audience might have is, how many projects are you actually involved in the end? You just mentioned one or two. Oh, I'm sure I counted at least 10 by the time. But I think, anyway, we're up time-wise. So thanks for sticking with us. Thanks for some questions from the audience. And thanks to the panelists here. Yeah.
Thank you.
Thank you.